Hello class and welcome back to math. Linear combinations and spanning sets. Linear combination definition. A linear combination of vectors is the sum or difference of scalar multiples of those same vectors. For example, root 2i minus 3j is a linear combination of I and j. Or negative 5i plus 2 pi j minus 27k is a linear combination. A spanning set. A spanning set for a space is a set of vectors such that for every vector in the space can be expressed as a linear combination of the spanning set. For example, I and j, they span two space, R cross R. The definition of a basis, well, a basis is a spanning set. It's just a spanning set that has the fewest possible number of elements. So, by the way, for 2 space, a basis would have 2 non-collinear vectors. Note, these 3 vectors do form a spanning set for 2 space. Because 1, 0, 0, 1 is the standard basis, so it forms a spanning set. But any 2 non-collinear vectors form a spanning set. So certainly all 3 of these form a spanning set, but they don't form a basis. Because a basis for 2 space would just be 2 vectors, and I see 3 here. By the way, any 2 of these does form a basis of 2 space. Example, explain why those 2 vectors, 6, 9, and 8, 12, do not span R cross R. Well, we examine them and we see that 6 to 9, we kind of think 2/3. 8 to 12 kind of looks like 2/3. We observe these 2 vectors are both multiples of 2, 3, which means that they are multiples of each other and are parallel, collinear. So 2 parallel vectors can't form a spanning set of a plane because any linear combination of them will also be parallel to them. What these 2 vectors do span is a line. One space, if you will. Here's an exercise. Pick any 2 non-collinear vectors in R cross R. So minus 5, 2, and 7 minus 3 would be an example of that. We know for sure that these are non-collinear because 7 over 5 does not equal 3 over 2, so they're not multiples of each other. These were multiples of each other. 8 over 6 does equal 12 over 9, so they do not span the plane because they're multiples of each other. We want to prove that these vectors span the plane. In other words, we want to prove that this is a spanning set for the entire R cross R and will therefore be a basis. Proof, let xy be any vector in the plane, and suppose that xy is a linear combination of the other 2, of these 2 vectors. If we can find A and B to satisfy this, then we have expressed any vector as a linear combination of the other 2, and we've proven that they span the plane. So if you see this equal sign, the x-coordinate on the left is x. The x-coordinate on the right is minus 5a plus 7b. See this y-coordinate? On the left it's y, and on the right it's 2a minus 3b, which leads to these 2 equations. X on the left must equal this from the right, and y here on the left, I put it over here, is equal to the y-coordinate here on the right, which is 2a minus 3b. Now what we need to do is the big rearrange. The system is solved for x and y. We want this to be a and b. So we'll rearrange. Carrying it forward, multiplying the first equation by 2 and the second equation by 5 to make these 2 look the same. performing the operation of addition. This is called elimination, by the way. Performing addition eliminates the a's and leaves us adding now 14b minus 15b, which is minus b, and 2x plus 5y. Multiplying through by a negative, we get b equals negative 2x minus 5y. Subbing this into, I said 2, but it could be 1. In fact, it could be anything. So we'll take this and sub it into 2. 2a minus 3 times b. b is this bracket because it's minus 2x minus 5y. Expanding and collecting like terms. And we got 2a equals minus 6 plus 4 minus 14y. Divide through by 2, and we have a. We have our a, we have our b. And what does this prove? It shows that for any xy, there exists a unique a and b such that xy could be expressed as a linear combination of those two vectors that we have. So it follows that negative 5, 2, and 7 minus 3 do span that plane as required, because I found a and I found b in terms of x and y. Now suppose we were going to do this exact same question again, and I chose those two vectors that we know to be actually multiples of each other. So these do not span the plane. I said these spanned one space or a line. What would happen if we said, well, I didn't notice that. I'm going to try to show that they actually span the plane. Let's see what happens. Let xy be any vector in the plane, just like before. Suppose that xy equals a linear combination of the two vectors, just like before. Generate the two equations and two unknowns. So our question is, can we find a and b to satisfy this? So we'll generate these two equations in the two unknowns. On the left, we have x equals 6a plus 8b, and y equals 9a plus 12b. Carrying it forward, this system is solved for x and y. We want to try to solve the system for a and b. Let's see what happens. Carrying it forward. Now, I'm going to do elimination again, just like before, except I'll take equation number 1. I'm going to turn both of these into 18s. I'll take equation number 1 times 3, makes 18a plus 24b equals 3x, and turn this one into times this one by 2, so it'll be 18a plus 24b plus 2y. Draw the line, and this time we'll subtract, because we want to eliminate the a's. We made them both 18 so that we could eliminate by subtracting. But the problem is the b's, they also subtract to 0. And so we got 0 equals 3x minus 2y. You see, when we did elimination, we inadvertently eliminated them both. And this leads to this. 3x must equal 2y, and so x has to be 2/3 y. X must be 2/3 y. And so, since x must be 2/3 of y, x is often not 2/3 of y. So this doesn't work for all x, y in the plane. This shows that there are x, y for which there does not exist real numbers a and b, such that x, y is that same linear combination of 6, 9, and 8, 12. So it follows that 6, 9, and 8, 12 do not span the plane as required. Oh boy, there's a lot to digest here. Coplanar definition. Coplanar, kind of like collinear or concentric circles. They share the same center. Collinear points share the same line. Coplanar vectors share the same plane. When two or more vectors are coplanar, it means they all lie on the same plane. Just as any two points are collinear, we know that any two vectors are coplanar. The question is usually, does the third vector also lie in this plane? This is what I'm talking about. Consider, say, a blackboard. And let's call those points. Now, given any 2 points, any 2 points are collinear. It says right here, just as any 2 points are collinear. So any 2 points, no matter where they are, I can take a ruler and I can draw a line through them. And the question arises, if I put a third point on that blackboard, is it on that line? So if I didn't see them, I would have to get the equation through the 2 points, and then take this third point, sub it into the equation, and see if it satisfied it or not. That would be the procedure if I couldn't see the points. All right, let's consider vectors. There's 2 vectors. Now, it says just as any 2 points are collinear, we know that any 2 vectors are coplanar. These 2 vectors define, or in fact span, this blackboard plane. Any 2 vectors define a plane. Now suppose this point right here, the tail of this vector, was anchored to the blackboard, and I came up and pried that vector out. Pried it out, pulled it out, so it was pointing straight out of that blackboard. Those 2 vectors would still span a plane. It would just look more like a table because the blackboard would have to lie flat on those two vectors, one of which is sticking straight out into the room. So 2 vectors define a plane, just like any 2 points define a line. And the question becomes, if there's a third vector, does it lie within this plane or does it pierce through that plane, like an arrow shot from archery? So that's what the question becomes here. Does it lie within or does it pierce through? So to determine if three vectors are coplanar in R cross R cross R, here's the procedure. Express one as a linear combination of the other 2. This generates lots of equations, 3 of them, an extra equation in just the 2 unknowns, A and B. Solve any 2 of those equations to get the unknowns, and then test the third equation and see if it works. Now, that all one really has to remember is express one as a linear combination of the other 2, and the other 3 steps will follow naturally. So here's an example. Here's 3 vectors. Determine if they are coplanar. Express one as a linear combination of the other 2. So I took this first one and I expressed it as a linear combination of the other 2. And this generates 3 equations. This 2 must equal 4a minus 8b. That minus 3 must equal minus a minus 3b. And that 5 must equal minus 3a plus 19b. Pick any 2 of those equations. I picked those 2. And then do the math. So it's just 2 equations and 2 unknowns like in grade 10, which I did, and I'm going to take for granted that you can do that too without showing all the work. In this case, you would show it if you were writing a formal paper. And it became A equals 1.5 and B equals 0.5. I suggest that you pause the video and do that math for yourself. Take that and sub it into the left side here is 5, but the right side is minus 3a plus 19b, but a is 1.5 and b is 0.5. Do that math on a calculator if you need to, and you'll get the right side equals 5, and therefore left side equals right side. And this, by the way, is the proper way to check. You separate the sides. And we can conclude that yes, that third vector does lie within the plane of the first 2.